In this picture, I've drawn this red tangent line to the graphed equation y equals f of x at x equals a. Now, I want to play a little bit with this. With my blue pen, I want to plant my foot, or my feet plural, at the point a comma f of a. Move a small distance to the right. I'll call it delta x. We typically use the uppercase Greek letter delta for small change. Now from there, I'll go straight up to the curve. And let's just pretend I move vertically upwards delta y units to get to that point on the black curve. So I hope you agree that in my pretty picture, it certainly is the case that f evaluated at a plus some small change in the x direction really is nothing more than the y coordinate of the point when x is equal to a increased by a certain change in the vertical direction. Now, sometimes computationally speaking, this small change in the y direction is difficult to compute, so we cheat. And we say instead, let's go back to the pretty picture. From this point located at a f of a, let's move a small change in the horizontal direction. Let's call it dx. But I have to admit, the way I drew my dx, I really meant to imply it's the same as delta x. And let's move up vertically a certain number of units to get to the next point, not on the black curve, but on the red tangent line. And I'll think of that vertical deviation as dy. So I'm using d's for changes from one point to another on the tangent line, deltas as changes from one point to another on the black curve. Now, even though dx and delta x are the same, dy and delta y are not. But if dx, that's delta x, is relatively small, I think the difference in this red and blue quantity is going to be negligible. And so I do think I can approximate this output, my goodness, in the following fashion. So this is approximately equal to f of a plus dy. I'll refer to dy as my independent differential. But you have to admit that red triangle is a right triangle. And so it certainly is the case that rise over run, dy over dx, these are actual small quantities. That's not a derivative. I'm not talking about the derivative for y respect to x. I'm talking about the ratio of these differentials. The ratio of these two quantities is nothing more than the slope of the tangent line because it's rise over run. But the slope of the tangent line is just this. And so this independent differential is f prime of a times my independent differential dx. Treat this literally as your man-made definition of what the differentials are. I will define my independent, excuse me, I misspoke. I will define my dependent differential as a product of f prime of a with my independent differential. So look at my dy up here. It's got another name. And so sometimes I can approximate outputs to functions by using that relationship. Let's actually do it. Let's pick the closest perfect square to 38. I think it'd be 36. But that's this. But that's this. Actually, I lied. It's not. But it's approximately this. But that's this. Now, the function f is this. So here's the square root. So I think I've got the square root of 36 plus f prime of 36, which is this. That dx is that small deviation in the x direction. But it's not going to give me this. Now, if you don't mind, can I just very quickly, I didn't do this ahead of time, I should have. Can I approximate to my calculator? Let's see. You got to really look at how close this is to what I have. I think using differentials to approximate this is as accurate to the third decimal place. That's really good accuracy. Now, I cheated. Me, the person who made up this question, chose a function where way out there when x equal to 36, that square rooting function is getting pretty close to being linear. I'm exaggerating a little bit. And so I do think I chose a value large enough for x so that my approximation was darn good.